Welcome back. This is Mr. Erlin. We are now talking about section 10.3 in geometry regarding circles. And we learned about terminology last time. Now we're going to see how these things interact together. So we'll start with some definitions. We've talked about a chord as a segment with endpoints on the circle. And now we're defining it as bisected when it's cut exactly in half. And like we learned way long ago, what it is that bisects that is up in the air. It could be a segment, it could be a point, it could be a lot of things that bisect it. Just the fact is, it's been cut in half. Turns out that this arc that has the endpoints, the same as the endpoints of the chord, is called a corresponding arc to this chord. So chord BC with a segment over the top corresponds to arc BC with an arc over the top. With those pieces and names in place, we can start talking about some theorems. The Congruent Corresponding Chords Theorem says that if I've got a circle and two chords are the same, they're congruent, then their corresponding arcs are also congruent. And it works bilaterally, so that if the arcs of two arcs in a circle are congruent, then the corresponding chords to those arcs are also congruent. We've also got something called the perpendicular chord bisector theorem, which states that if I have a chord and I intersect it in such a way that it is through the center, in other words, I'm using a diameter or a radius that is perpendicular to it, there's three components. It's a radius or diameter, contains the center. It is bisecting this chord, and it makes a right angle. And if I have any two of those, the third must be true. So if I've got a chord and another chord that bisects it and is perpendicular, then that chord must contain the center or be a diameter. Version 2, if I have a chord that is bisected by something that contains the diameter, then it must be a right angle. Number 3, if I have a diameter that is perpendicular to any chord, then that chord is bisected. And then an ancillary piece of that, or corollary to that, would be if you are able to prove that these two components are the same, this is reflexive, these angles are both right angles, therefore these little triangles are congruent, so these segments, FG and GD, are congruent. And if the segments are congruent, the chords are congruent, then like we said a moment ago, the corresponding arcs must also be congruent. This is the converse of that theorem. Another one is the Equidistant Chords Theorem, suggesting that if I have two chords in a circle that are the same length, then their distance from the center of the circle will be the same. We could prove this by drawing a radius to each of the endpoints. If the chords are the same length, and we look at the distance, which is through the center and perpendicular, it must bisect those. If these chords were the same length, then the bisected portions are the same. These are radii, which are the same. These are perpendicular because we're saying it's a distance. Therefore, by RHL or HL, these two triangles are the same. Therefore, their distances from the center are the same. This is a challenge problem that asked us to find the measure of an arc. Let's do a blank one so it's easier to see. Find the measure of an arc given the information they were given. And they tell us that there are three parallel chords. And they tell us the lengths of those chords are 26, 24, and 10. Well, we know that this one is going through the center, which makes it a diameter, and the diameter will be the longest chord in the circle. So if one of them is 26, the others are shorter, this one must be 26. And as I work my way out, they get shorter until I'm furthest out, that's my lowest one. If I were to draw a radius that intersects all of these chords in a right angle, as we just learned, that then bisects each of these chords. Since we knew this one was 26, that makes this 13. If this whole thing was 24 and it's been bisected, that makes this 12. And if this was 10 that's been bisected, that makes this 5. The question before us is how we find the measure of this arc. Well, the only way we could find the measure of that arc from what we're given here is if somehow we were able to find the measure of that central angle. Remember that the measure of a central angle is equal to the measure of the arc. So we are going to find the measure of that central angle, and the way we're going to do it is I'm going to recognize that I can make a right triangle there, and I know that this base is 5. This is the radius. And although I don't see what that number is exactly, I know from up here that this is the diameter of 26, having been bisected as 13. Therefore, every radius in this circle is 13. So what I'm looking at here is a little right triangle, where this is 5 and this is 13, and I don't know that. But I can use Pythagorean Theorem, because it's a right triangle. This turns out to be one of our Pythagorean triples, so I should know this off the top of my head, but just in case I didn't, I can do subtraction, and x is equal to 12. And 5, 12, 13 is one of our Pythagorean triples. So this is 12. Now, the problem is, I now have this triangle, but what I'm looking for is this angle over here. Turns out, I'm creative about this, I can do the same thing I just did with finding that triangle, but find this little triangle, this pink one. And if I can find that little triangle, and find this angle measure, that would be all the way here. And then if I subtract out the little greens angle, what I'd be left with, take away that green triangle, what I'd be left with is the amount of the angle that is my central angle I'm looking for to give me this arc. Well, since this pink triangle has a side length of 12 here and a radius of 13, it's actually the same triangle. It's a congruent triangle, 12, 13. That means this part must be 5. So if I call this angle A and this angle B in my 5, 12, 13, what we're really talking about is taking the bigger one, angle B, and subtracting the little one, angle A. So now going back to what we learned last unit, if this is A and this is B and this is 5, 12, and 13, trigonometry will let me find those values. To find A, I'm going to put my eyeball up there. Relative to A, this is opposite, this is hypotenuse. I could go anyway. But I'm going to go opposite in the hypotenuse, which is our sine function. And the sine of an angle is equal to the opposite over the hypotenuse. So the sine of A is equal to 5 over 13. If I want to find A, I'll do the inverse sine to both sides. And I'll get A is equal to the inverse sine of 5/13. And to do B, I could do the same thing, but instead of sine, I would say relative to B, 5 is now adjacent, and 13 is hypotenuse. So that means cosine, ha. So the cosine of angle B is equal to 5 over 13, which means B is the inverse cosine of 5/13. If I plug this into a calculator and get a decimal approximation, this comes out to be about 22.62, whereas the other angle is about 67.38. Not surprising that they're complementary, they add up to 90 because they're the two non-right angles in a triangle. And what the angle I'm looking for, this one over here, is the big one minus the little one. So B minus A. So the measure of BC is equal to B minus A, which is 67.38 minus 22.62, which is 45.24. So that's right, so 67.38 minus 22.62. 44, oops, I'm way off here. 67.38 minus 22.62 comes out to be 44.76 degrees. So that's the answer. Pretty challenging problem, but asking you to think a little bit more about these from a different perspective. Thank you.